I love, love, love this problem. You guys know I love the molecular scenes problems anyways because they help us think about concepts. But this one in particular, I think really, hits home because it's a process that you can make sense out of and kind of, rationalize and internalize because it has to do with water and phase changes for water that, are real to your everyday world. So as it tells us here, the following scenes represent a familiar phase change for water, right? So in this case, we've got, hopefully everybody's good realizing that's gaseous water, and that's water as a liquid. So the first part of this problem asks us to think about the signs of delta H and delta S for this process and to kind of explain. All right, so let's think about the delta S term first. So we can see here that going from a gas to a liquid, our molecules are moving less. So delta S must in that case be unfavorable. It's going to be negative. So negative is unfavorable. Our molecules are moving less. And that's always going to happen when we go from a gas to a liquid, or as I'll discuss when I wrap up this problem, a liquid to a solid. So our entropy is unfavorable for this process as written. So let's then think about enthalpy. This one might be a little bit hard to think about right out of the gate, but taking a gas and condensing it as a liquid, there's less energy, there's less kinetic energy in these liquid molecules. So that must mean heat was given off. If heat's given off, that's an exothermic reaction, and that again is favorable. An exothermic reaction. And I know sometimes it's hard to think about gas condensing as giving off heat and being exothermic. But if you're ever confused, what this means is if we reverse the process and we wanted to take a liquid and make it go into a gas, that we have to add heat. Well, sure, that makes sense. You want to boil a liquid, you need to add heat. Okay, so that helps us rationalize that yes, heat belongs on this side of the equation. Heat on the right side as a product means it's exothermic. Exothermic reactions are favorable. Okay, so that answers part A. What are the signs of delta H and delta S? So the question is this reaction spontaneous at all temperatures, no temperatures, low temperatures, or high temperatures? And this is the idea of this binary system that we have between favorable, unfavorable for entropy, favorable, unfavorable for enthalpy. It all comes down to, again, this equation. If we want a reaction to be spontaneous, that means delta G must be negative. Well, a win-win situation means that enthalpy is negative and entropy is positive. That means mathematically we're going to take a negative term and we're going to subtract something positive from it, which means it's going to make it even more negative. So again, this is going to be our win-win situation. We don't have that situation. Win-win situations means that there's any temperature we can be favorable at. That's not the case here, okay? Now, a lose-lose situation would be an endothermic reaction that has an unfavorable entropy. Again, this is going to be our lose-lose situation. Those reactions are going to be favorable at no temperature. There's no temperature that we could get to that would make that reaction spontaneous. So anytime you don't have a win-win or a lose-lose means you have one of the win-lose combinations. The win-lose combination we have is that enthalpy is favorable, it's negative. Entropy is unfavorable. So this again is a win-lose situation. The other win-lose situation, which is really the lose-win situation, is where you have an endothermic reaction that has favorable entropy. So again, this is the lose-win situation. What we see with these processes is that there is a temperature dependence. So we're not in the lose-lose situation. We're not in the win-win situation. We're in one of the win-lose situations, which means we have a temperature dependence. Now, we need to think about whether this process is favored at low temperature or high temperature. So what we need to do is think about whether or not the entropy term is helping us. So see if this makes sense, right? We're in this situation where our entropy is not helping us, right? We're subtracting off a positive value here, which kind of diminishes the contribution from our favorable entropy. So mathematically, we'd like to diminish the contribution of this T delta S term. We do so by decreasing the temperature. Okay, so in this situation where we have an exothermic reaction with unfavorable entropy, it's going to be favored at low temperature. On the other side, if we had an endothermic reaction, right, that had favorable entropy, this is the guy that's helping make this reaction spontaneous. So we want to supplement and augment this term. In that case, we'd like to have higher temperatures. That isn't the situation that we have. We have low temperatures. Okay, why I love this problem is we have kind of a real life think about that allows us to make sense out of this, right? If you have water vapor and you like to condense it, do you want to have a cold, mug that you took out of the freezer? Or do you want to have, a hot cup of tea? Which is going to condense water? Clearly the cold temperature, okay? The cold glass is going to do that. So this process is favorable at low temperatures. Okay, again, a great problem because we can tie in kind of the theory of entropy and enthalpy compensation, but we have a real life kind of internal logic check that we can think about. All right, the last little thing I want to think about is, well, wait a minute. Isn't it kind of spontaneous to go in this direction? Right? Let's reverse the reaction. What happens if I take a liquid and make it go to a gas? Right? In that case, we'd have this situation. We'd have an endothermic process where the entropy was helping us. We just said that that is going to be favored at high temperature. That makes sense, right? If you want to take water that's a liquid and boil it, you want to increase the temperature. So what we have here is what I like to think about as a pivot point. There is some point, a tipping point, where we change the spontaneity of this reaction. And hopefully it makes sense to you guys that for this process, it's 100 degrees C. When we are below 100 degrees C, the direction as written here is favored. We're going to favor gas condensing into a liquid. And we know that if we've got water vapor that we've boiled and it finds a temperature that's less than 100 degrees C, that liquid or that gas is going to condense as a liquid. Conversely, if we're above that temperature, right, we're going to be able to continue to have that water exist in the gas phase. And we're going to even favor the production of more gas molecules by volatilizing that liquid water. So to just kind of wrap this up again with another example here, right? The example that I kind of summed up in class and talking about another pivot point that we think about for water, which is 0 degrees C. Let's think about not liquid going to gas, let's think about solid going to liquid. If we want to take solid water and make it liquid, we need to add heat to it, right? That's melting ice. From an enthalpy standpoint, enthalpy is positive. That's an endothermic reaction. That's unfavorable. That's a lose. Entropy, however, in going from a solid to a liquid is favorable. It's positive. So again, here's our positive situation. We will have temperature dependence. And because entropy is what's helping us, we want to supplement that. So we're going to favor that by higher temperatures. Well, of course we're going to favor the melting of ice when we increase temperature. That makes sense. Looking at the flip side, right, if we reverse this reaction and talk about liquid water, making it into solid and giving off heat, actually freezing water is an exothermic process. The enthalpy for this, again, being negative means that it's favorable. But now since we've taken a liquid and made it sit still as a solid, from an entropy standpoint, those molecules are moving less. That's unfavorable. So, but for this win-lose situation, we want to discount and, diminish the contribution from entropy, which was not helping us. So in that case, we want to decrease the temperature. The spontaneity of this process will be favored as we decrease the temperature. Of course, right? You want to freeze water and make an ice cube. You don't increase the temperature, you decrease it. So again, a great problem to think about entropy, enthalpy compensations. And because of the context that it's in, thinking of water as the molecule in phase changes, we have a great context for it to make sense for us.